Welcome to lecture session for diploma students. In today's lecture, we are going to analyze the parallel resonance phenomenon. So, in this chapter, we have two different networks for analysis. Both are parallel networks. The first one is having a resistance, inductance, capacitance all connected in parallel. So, you have three different currents passing through the passive elements. One is IR, the other one is IL and then IC. Whereas here is also a parallel network, but in the first parallel branch you have a capacitance, in the second parallel branch you have the series combination of a resistance and an inductor. So, a variable frequency is applied across the circuit. At a particular frequency, the relative component of the line current becomes 0. This frequency is called as the resonant frequency. When total current is in phase with the supply voltage, parallel resonance is said to occur. This is true only if reactive component of inductive branch current is equal to the capacitive branch circuit. So, the phasor is like this. So, V is taken as the reference phasor. So, in this network it is a combination of a series combination of R and L. So, we have already learnt that whenever you have a purely inductive circuit, then the current value, the current phasor will be exactly lagging behind the voltage by 90 degrees, but due to the presence of R and L, so you have a phasor of I like this, lagging behind the voltage by an angle phi. So, this is your IL. Then where will you mark the IC? So, you can see here. So, this is your IC, it has a purely capacitive network, capacitive branch. So, there is no combination of R plus C. So, it is a pure C. So, R is not there. So, if that is the case, you have IC exactly perpendicular, that is 90 exactly at 90 degrees with the applied voltage. Now, I will once again repeat, if there is no resistance here in one branch, then you should have drawn this IL exactly perpendicular to this V, that is lagging behind the applied voltage. Due to the presence of R and L, the phi, that is angle between the voltage and the current IL, will not be exactly equal to 90, but it is less than the value of 90. So, I have drawn the phasor IL here. So, this is your phi. Then considering the other branch, you have a pure capacitor. So, in a pure capacitor, the current will be, that is the capacitor current will be leading the voltage by 90 degrees. So, this is the voltage reference. So, you have to draw the capacitance current here. Now, what is the total current I you see here? So, I is equal to the total current I is equal to IL plus IC. So, it is not the algebraic addition, it is the vectorial addition or phasor addition. So, what I am going to do is I am going to apply parallelogram law of vectors to add these two phasors. How to draw the parallelogram law of vectors? Right from IC you draw a parallel line to IL. Similarly, you draw a parallel line to this IC, both will intersect at one point. So, that is marked as your I, that is the total current. So, this is how you should find out the resultant of the total current. So, again Q factor, at resonance the current in the branches of the parallel circuit can be many times greater than the supply current. You can see here, at resonance the current in the branches of the parallel circuit can be many times greater than the supply current. The factor of magnification in the parallel circuit is called as Q factor, it is also called as the current magnification. Unlike the series RLC circuits, wherein you have the quality factor expression is entirely different from this one, where the voltage magnification occurs in a series RLC. Here the magnification is happening, but in a different parameter, which is current magnification. So, the Q factor or current magnification is equal to current in the inductive or capacitive branch divided by current in supply at resonance. So, Q factor is equal to either IL or IC divided by I. So, IC is equal to V by XC, which is equal to V into 1 by XC. So, which is nothing but I am going to substitute, this is V by XC. So, I am going where XC is equal to 1 by 2 pi FC. So, what I am going to do right now is, instead of this XC I am going to substitute 2 pi FC. So, it is V into V divided by 1 by 2 pi FC. So, this 2 pi FC will come to the numerator. So, you will have 2 pi FC into V divided by 1, or it is 2 pi FC into V. What is 2 pi FC? We know that 2 pi FC is equal to omega. So, this is the angular frequency, omega is the angular frequency. Now, instead of this 2 pi FC I am going to substitute omega here. So, you have omega into CV. Then I is equal to V by Z naught, Z naught is the impedance, V is the applied voltage. Now, what is Z naught? Z naught is equal to L by CR. So, bringing the CR up to the numerator, we have VCR divided by L. Then substituting F naught is equal to 1 by 2 pi into square root LC, which is a resonance frequency. Then Q factor becomes 2 pi L. So, here it is IC by I. So, you have 2 pi L divided by 1 by square root of LC into R. So, upon simplification you have 1 by L by R into square root of LC. So, this L I am splitting it into 2, square root L and square root L for cancellation of these two components. Then you have 1 by R square root of L by C. So, the same expression for Q factor, whereas the only difference is there in series RLC circuit voltage magnification occurs, voltage magnification in series, whereas here in parallel current magnification occurs. Current magnification occurs in parallel. Condition for parallel resonance. The reactive component of inductive branch current is equal to the capacitive branch current, which means that IC should be equal to IL. So, the resonance frequency at resonance IC is equal to IL sin phi L. We know that IC is equal to V by XC, where V is the applied voltage, XC is the capacitive reactance. What is IL? V by ZL. Sin phi L is equal to XL by ZL from the phasor diagram. V by XC is equal to V by ZL into XL by ZL. So, you need to calculate XL and XC. So, it will be some ZL square. So, you cross multiply this, ZL square into V is equal to XL XC. XL XC, ZL square V is equal to XL XC. So, here also V will be there. So, V ZL square, so XL XC into V. So, V gets cancelled. So, you have ZL square is equal to XL XC. So, this is the expression. Then I am going to substitute XL is equal to 2 pi FR into L and XC is equal to 1 by 2 pi FR into C in this equation. So, when you substitute those parameters, then ZL square is equal to this. So, ZL square will be is equal to L by C, because this 2 pi fr, this 2 pi fr will cancel each other. So, ZL square is equal to L by C. So, what is ZL square? ZL square is equal to R square plus XL square. So, substituting the value of R square plus XL square in the place of ZL square, and then we know that XL is equal to 2 pi FR L. I am going to substitute the value of XL here, then I am keeping this 2 pi FR L the whole square on the left hand side and bringing this R square to the right hand side, it becomes minus R square, then 2 pi FR the whole square is equal to 1 by LC by. So, what I am doing is I am multiplying this with R by L square. If you multiply L by C, so this L get cancelled. So, you have R by CL here. Now, 1 by you are taking square root on both sides, 2 pi FR is equal to square root of 1 by LC minus R square by L square. So, the resonance frequency value is 1 by 2 pi square root of 1 by LC minus R square by L square, because I am bringing this 2 pi to the right hand side. So, this is the expression for resonance frequency. Then what is the impedance at resonance? The effective resistance of the RLC parallel circuit at resonance is called the dynamic impedance or the dynamic resistance. At resonance, IR is equal to IL cos phi L. We know that IR value is equal to V by ZR, where V is the applied voltage and ZR is the impedance. So, IL is equal to V by ZL, cos phi L is equal to R by ZL. So, V by ZT is equal to V by ZL into R by ZL. So, from that you find out 1 by ZR is equal to R by ZL square. So, 1 by ZR is equal to R, I am bringing this C down. So, it is R by L by C. So, this is a single term. Then ZR is equal to the reciprocal of L by C by R, which is equal to L by CR. So, the entire circuit behaves as a non-reactive resistor of L by CR ohms under resonance. The quantity L by CR ohm is often called as the dynamic impedance or dynamic resistance. So, the graphical representation, it is the line current versus the frequency. You can recall the line current versus frequency graph for series, it will be like this inverted U curve. So, this is the frequency and this is your current, whereas here it is exactly the opposite way. So, at parallel resonance, the line current IR is minimum and is given by, here in series the line current is maximum, but impedance is minimum, whereas here exactly opposite, at parallel resonance the line current IR is minimum and is given by IR is equal to V by ZR, where ZR is equal to L by CR. The small current is only the amount needed to supply the resistance losses in the circuit. So, the characteristics of parallel resonance, this is the current versus frequency and this is the admittance versus frequency, both are alike here. So, exactly at the resonance frequency the current is minimum. So, this is also called as a rejector circuit. The lowest current from the source occurs at the resonance frequency of a parallel circuit, hence it is called as a rejector circuit. Now, let us see the few properties of parallel resonance. At resonance, the net reactance is 0. Number 2, at resonance the impedance is maximum. You compare this with series, whereas the impedance is minimum. In a series resonance circuit the impedance is minimum, whereas here in the parallel resonance circuit one of the properties is at resonance the impedance is going to be maximum. Also at resonance the current is minimum. You compare this with the series circuit, the current is maximum there. Fourth point is at resonance the power factor of the circuit is unity. Fifth one is it magnifies the current. What happens in the series resonance circuit? It magnifies the voltage, whereas in parallel resonance circuit, it magnifies the current. Then line current is in phase with voltage. Now we will have a small comparison between the series and the parallel resonance circuit. The criterion for comparison, first one is the impedance at resonance. What happens in the series circuit? It is minimum, whereas in a parallel circuit it is maximum. Current at resonance is maximum in the series circuit, it is minimum in the parallel circuit. What happens to the effective impedance at resonance? Effective impedance is equal to R, whereas it is equal to L by C into R. What is the resonance frequency in a series circuit? It is 1 by 2 pi into square root L C, whereas here it is 1 by 2 pi into square root of 1 by L C minus R square by L square. It magnifies the voltage, the series resonance circuit magnifies the voltage, whereas the parallel circuit magnifies the current. What happens to the power factor at resonance? It remains as unity, here also it remains as unity. Quality factor, that is Q factor, expression is omega L by R, here also it is omega L by R. Other name, it is called as acceptor circuit and this is called as rejector circuit. The application of resonance used in oscillator circuit to provide different frequencies, used in tuning circuit of radio and TV to obtain the required station. Now we will move on to few examples, we will do some example problems based on the parallel resonance. A coil of 10 ohms resistance and 0.1 Henry inductance is connected in parallel with a capacitor of 100 microfarad. Calculate the frequency at which the circuit will act as a non-inductive resistance of R ohm. Find also the dynamic resistance. Now first of all we will write down the given data. So the connection is basically a parallel connection or a parallel circuit. Resistance value is 10 ohms, inductance is 0.1 Henry, capacitance is 100 microfarad or 100 into 10 power minus 6 farad. We need to find out the resonance frequency and the dynamic value of resistance. What is the resonance frequency expression? It is 1 by 2 pi into square root of 1 by L C minus R square by L square. L value is 0.1 Henry, C value is 100 microfarad, 100 into 10 power minus 6, then R value is 10, L value is 0.1. So, 10 square by 0.1 square. By minimizing this and simplifying this, you will have 47.77 hertz. So, the resonance frequency of the parallel circuit is given by 47.77 hertz. Now, how to find out the dynamic resistance? We know that the value of dynamic resistance, that is the expression for dynamic resistance, is L by CR. L is equal to 0.1 Henry, C value is, we know that it is 100 microfarad, R value is 10. Substituting all these parameters and simplifying, we get the dynamic resistance value, that is RD is equal to 100 ohms. So, the resonance frequency is given by 47.77 hertz and the dynamic resistance value is equal to 100 ohms. Now, let us move on to the next problem. A parallel circuit consists of a 2.5 microfarad capacitor and a coil whose resistance and inductance are 15 ohms and 260 millihenry respectively. Determine number 1 the resonant frequency, number 2 the Q factor of the circuit at resonance, then dynamic resistance of the circuit. So, first of all we will write down the given data. The connection is a parallel connection, resistance value is 15 ohms, inductance is 260 millihenry or 2 power minus 3 Henry, sorry 260 into 10 power minus 3 Henry, capacitance is 2.5 microfarad, 2.5 into 10 power minus 6 farad. So, we need to find out 3 parameters, one is a resonance frequency, second one is the Q factor, third one is the dynamic resistance. So, the expression for dynamic resonance frequency for a parallel circuit is known to us. It is expression given by 1 by 2 pi into square root of 1 by L C minus R square by L square. So, we know the values of resistance, inductance and capacitance. So, substituting all those values in the formula and upon simplifying you get the resonance frequency value as 197.3 hertz. Then the next step is you need to find out the quality factor. So, though the quality factor expression is same as that of the quality factor expression of the series resonance circuit, in series resonance also it is same 1 by R to square root of L by C. The main difference is, though this expression remains same, this into the value of current you need to find out. So, it magnifies the current, whereas in a series circuit it magnifies the voltage. The quality factor basically magnifies the current here. So, 1 by R, so it is 15 ohms resistor, L value is 260 into 10 power minus 3 Henry, and the capacitance value is 2.5 into 10 power minus 6 farad. So, substituting all the parameter values and simplifying, you have the Q factor as 21.49. It means that the current is magnified, that is the total current is magnified 21.49 times the value of the current passing through the inductor or capacitor. Then we need to find out the dynamic resistance, whose value is equal to L by CR. L value is 260 into 10 power minus 3 Henry, then C value is 2.5 into 10 power minus 6 farad, and R value is 15 ohms. So, mere substitution of all these values and simplifying, you get the dynamic resistance value as 6933 ohms. Now, the resonance we can summarize, the resonance frequency value is 197.3 hertz, and the dynamic resistance RD value is 6933 ohms, and the Q factor is equal to 21.49. Now, we will move on to the third example here in a parallel resonance circuit. An inductive circuit of resistance 2 ohms and inductance of 0.01 Henry is connected to a 250 volts 50 hertz supply. What capacitance placed in parallel will produce resonance? So, this problem is something different from the previous two problems what we have done already, because they have not, in that they have given all the parameter values R, L and C, whereas here for a condition of resonance to happen, what is the value of capacitance we need to find out. So, that is the only difference. Find the total current taken from the supply and the current in each branch circuits. So, first we will write down the given data. One is the connection is a parallel circuit, resistance value is 2 ohms, inductance is 0.01 Henry, voltage is 250 volts, and the frequency value is 50 hertz. We need to find out the capacitance, total current and branch current. So, this capacitance value will be for a condition of resonance. Now, the resonance frequency, the value of resonance frequency is 1 by 2 pi square root of 1 by L C minus R square divided by L square. Then we know the value of, already the resonance frequency value is given, which is 50, then 1 by 2 pi 1 by, what is the L? It is 0.01, C value is not known, just substituting the C value, R value is 2 ohms and L value is 0.01 square, 0.01 we are substituting here, and simplifying, we are bringing this 2 pi over here to the left hand side. So, which is 50 into 2 pi, this is square root of 1 by 0.01 C minus 40,000. Again squaring both sides, squaring both sides, we have 50 into 2 pi the whole square is equal to this square root 2 will go off. So, 1 by 0.01 into C minus 40,000. So, expanding this and simplifying, bringing the C value C to the left hand side, we have the value of C as 721 microfarad. So, the dynamic resistance value is equal to L by CR, L is equal to 0.01, C value we have already found out, it is 721 microfarad, substituted that value and the resistance value is 2. We have the dynamic resistance value as 6.93 ohms. What is the total current? It is the applied voltage divided by the dynamic resistance. The applied voltage is 250, dynamic resistance value is 6.93. So, the total current will be 36 amperes. So, now we need to find out the branch currents. The branch current is XL is equal to, first we need to find out XL 2 pi FL. So, substituting the values of pi, frequency value is 50 and inductance value is 0.01 Henry, we get XL is equal to 3.14. Then we need to find out the capacitance, capacitive reactance, which is 1 by 2 pi FC. So, substituting the values of frequency and the capacitance value whatever we have obtained in the previous slide, which is 721 microfarad, we are getting XC value is equal to 4.42 ohms. Then current through the coil is equal to V by ZL, impedance is equal to square root of R square plus XL square. So, substituting those values here, we get the impedance value as 3.72 ohms. Then current through the coil is equal to applied voltage by ZL, which is equal to 250 by 3.72 will yield you 67.2 amperes. The current through the capacitor is equal to V by XC, which is 250 divided by 4.42, which is 56.56 amperes. Now, we will summarize whatever we have found out. So, for the condition of resonance, we have calculated the capacitance value, which is equal to 721 microfarad, and the current through the coil is 67.2 amperes, and the total current value is 36 amperes, and the current through the capacitor is 56.56 amperes. So, we will have a quick review of whatever we have studied in unit 4, that is resonance circuits. So, in this particular session we have dealt with the parallel resonance. So, here the passive elements R, L and C are connected in a parallel fashion. Then we have analyzed the corresponding vector diagram or a phasor diagram. Then we need we have found the expression for the Q factor, how we have analyzed how the voltage, that is current magnification, is happening in a parallel circuit. Then Q factor derivation we have made. Then we have derived the condition for parallel resonance. We have calculated the resonance frequency, which is Fr is equal to 1 by 2 pi square root of 1 by L C minus R square by L square. Then we have analyzed the impedance, what happens to the impedance at resonance. We have finally calculated ZR, which is L by CR, which is also called as the dynamic value of resistance. Then we have analyzed the graphical representation. We have compared the graphical representation of I versus frequency for both parallel circuit and series circuit. Then characteristics of parallel resonance we have analyzed. Then the properties of parallel resonance we have analyzed. Then we have made a short comparison between the series and parallel resonance circuits, and finally we did few problems on the parallel circuits, parallel resonance circuits, and finally we found the value of dynamic resistance, Q factor, resonance frequency, etc. Thank you.